Hello everyone, I'm Chris Lin from NOVOSENSE Microelectronics. Today, I'll cover three main topics. First, common types of motors and inductive loads with your applications. Second, introduction to NOVOSENSE's motor driver products. Finally, detailed explanation of motor driver chips and how they work. In our daily lives, motors are everywhere, often hidden inside devices. For example, in cars, motor drive systems like windows, seats, mirrors, tailgates, and door locks. Motors convert electrical energy into motion based on electromagnetic induction. They are mainly classified as brushed DC, brushless DC, and stepper motors. Relays and solenoids, like motors, are common inductive loads with similar drive principles. NOVOSENSE's motor driver chips are tailored to control these motor types. Brushed DC motor (BDC) is powered by DC and use mechanical brushes for commutation. They are cost-effective and simple to control but offer low precision and higher noise. BDC motors are widely used in automotive body controllers for side mirrors, doors, windows, seats, and electronic locks, where bidirectional rotation and speed adjustment are needed. Brushless DC motor (BLDC) differs from brushed DC motor by placing permanent magnets on the rotor and electromagnetic coils on the stator. They use voltage, frequency, and phase control to create a rotating magnetic field that drives the motor. BLDC motors offer high precision, efficiency, smooth operation, and durability, but are costlier and need complex algorithms. Common applications include automotive systems, fans, water pumps, and oil pumps. Stepper motor differs from brushed DC motor by using pulse signals for precise movement and position control, enabling micro-stepping. Known for high precision, smooth operation, and frequent start-stop capability. They are ideal for automotive headlamps, electronic expansive valves, HUD adjustment, and HVAC airflow controls. Relays and solenoids use magnetic effects from electrical signals to control high current or high voltage circuits, commonly found in automotive body systems, vehicle controllers, and PLCs. NOVOSENSE provides a full range of driver chips for brushed DC, bipolar stepper, three-phase brushless motors, and intelligent low-side switches. Solutions include gate pre-drivers and integrated MOSFET bridge drivers for design flexibility. Advanced features like current modulation and protection ensure convenient, safe, and reliable motor control. So how do motor driver chips actually work? This H-bridge motor driver chip features 4 MOSFETs in an H-bridge configuration. The outputs, out1 and out2, connect to the motor brushes, while the input connects to the control unit. By controlling the MOSFETs, the chip adjusts both the current direction and magnitude through the motor windings. The 4 colored lines represent the current paths for each of the motor's operating states. For forward rotation, MOSFETs HS1 and LS2 are turned on, allowing current to flow through winding L from left to right, driving the motor in that direction. When MOSFETs HS2 and LS1 conduct, current flows through the winding from right to left, driving the motor in reverse. When the motor is running in a forward direction, when LS1 and LS2 are on simultaneously, the winding current discharges to ground, enabling braking or slow decay. When LS1 and HS2 are on, a negative voltage across the winding causes the current to rapidly decay as it is absorbed by the power supply.
In motor control, the driver chip combines fast and slow decay to precisely control the motor current. Key parameters of these chips include VM voltage, max voltage rating, current capability, input control method, current modulation, sampling, and protection and feedback features. The following section uses the NOVOSENSE NSD7312 series DC brushed motor driver to explain these in detail. VM operating voltage, and maximum voltage rating. The NSD7312 operates from 5 volts to 36 volts, with a maximum voltage rating of 40 volts. Input control method. The NSD7312 has in-1 and in-2 logic inputs for PWM motor speed control, along with integrated PWM current modulation to reduce peak current during startup or with large capacitive loads, minimizing transient current spikes. Output current. The NSD7312 has a theoretical current capability of 3.5 amperes, but practical current capacity depends on factors like current duration, heat dissipation, power consumption, and ambient temperature. Current modulation and sampling. The NSD7312 integrates current modulation to limit the operating current to the set peak value, I-trip, via PWM chopping, and includes current sampling for real-time monitoring. Protection and feedback. The NSD7312 includes protection features like VM undervoltage, overcurrent OSP, overtemperature TST, and fault feedback. The H-bridge chip introduced above can drive a single DC brushed motor. We also offer multi-channel half-bridge chip solutions for driving multiple motors. The NOVOSENSE NSD-A308 series multi-channel half-bridge driver integrates 6 to 12 half-bridge drivers, offering flexible usage. These chips can be paired to create multiple independent H-bridges for driving several motors. They can be connected in parallel to boost the current capability or in series for time diversion multiplexing to drive more motors. Additionally, they can serve as high and low side switches for driving relays, LEDs, or small loads. The NSD-A308 series offers great flexibility, making it ideal for standardizing customer system designs and is widely used in automotive control applications. Key parameters of multi-channel half-bridge drivers beyond basic DC brushed motor drive specs include the number of channels, integrated PWM generator, SPI interface, and open circuit diagnostic protection. The NOVOSENSE NSD-A3 series offers 6, 8, 10, 12 channel half-bridge configurations with 8 integrated PWM generators, allowing PWM frequency and duty cycle to be configured via SPI. It also offers intelligent diagnostics to help automotive systems detect the load connection status. In case of disconnection or short circuit, the external MCU can access channel error info via the chip's internal registers. In addition to DC motor drive solutions, NOVOSENSE offers stepper motor drivers. This typical bipolar stepper motor driver integrates 2 H-bridge circuits to independently control the current direction and magnitude for the motor's 2 windings. By supplying orthogonal currents with microsteps to the 2 windings, we precisely control the motor's magnetic field vector for accurate position control. Higher current microstepping resolution improves stepper motor position accuracy and smoothness. Common configurations include 4-step, 16-step, and 32-step modes. For stepper motor driver chips, the key aspect is precisely controlling the output microstepping currents, in addition to the internal H-bridge drive. In 4-step mode, the current within a 90-degree electrical angle is divided into 4 microsteps, with sinusoidal waveforms in the 2 windings 90 degrees out of phase. The driver chip uses control algorithms and modulation circuits to precisely regulate the H-bridge, ensuring the motor winding current matches the desired waveform and magnitude, with output current sampled for feedback control. The key parameters for stepper motor driver chips include operating voltage, phase current magnitude, control signal type, maximum microstepping resolution, current modulation, decay mode, and protection features. NOVOSENSE offers the NSD-A381 stepper motor driver chip, supporting to 132 microstepping resolution. A dedicated video introduction will be available soon. More introductions and product demos on motor driver chips will be coming soon. Stay tuned for updates.